Okay, let's dive right into this. Welcome back to another explainer, where we treat the Cambridge syllabus like an archaeological dig. You know, it really is like being an explorer. Today, we're taking our shovels, our brushes, our pickaxes, and we are heading straight into the Cambridge physics curriculum. We're going to uncover the hidden clues buried deep inside those incredibly tricky exam questions. You know the ones I'm talking about? The ones where you read the paragraph and think, what are they even asking me? We're going to strip away that confusion layer by layer until we reveal the perfect full-mark answer. Whether you're sitting for the Core 0625, the Double Award 0651, the 0652, the O-Level 5054, or even gearing up for the AS and A-Level 9702, the examiner's mindset is exactly the same. If you've ever stared at a multi-part electricity question, felt your heart rate spike, and felt like you were trying to read an ancient, undecipherable language, I promise you, you are in the exact right place. We are going to decode the matrix today. But hey, before we start throwing around complex formulas and rigid textbook definitions, let's take a step back and ask a truly fundamental question. What physical effect, measurement, or prediction actually depends on understanding potential difference? Like, why does this concept even exist? We are bypassing the formal, rigid definitions just for a second because to truly master physics, the concept has to feel absolutely necessary to you, not just like some decorative piece of trivia you memorized. Why does this matter in the real world? Think about it. When you plug your phone into a charger, why does the battery actually fill up? What is doing the pushing? When we root the idea in a physical necessity first, the need for an invisible force to drive a physical effect, you become far less dependent on memorized wording. Instead, you become much more capable of reasoning your way through completely unfamiliar, weird exam scenarios. Because you aren't just reciting words, you actually understand the physical reality of the situation. So, here's our roadmap for today's dig. First up, we're looking at the core challenge. Second, we're going to introduce you to the four-step framework. This is a total game changer. Third, we'll explore cause and effect in physics. Fourth, we're going to practice escaping some of the most common exam traps that catch out thousands of students every year. And finally, we'll wrap up with quick recall mastery, giving you the tools to pull this information out of your brain instantly under exam pressure. Let's get to it. Section 1, the core challenge. Now I want you to imagine two archetypal physics students. We're going to call them Alex and Sam. They're both sitting down in that huge, echoing sports hall for a brutal physics exam. The clock is ticking away on the wall, the invigilator is pacing the aisles, and they are both staring down a highly complex, high-mark past paper question on electricity and potential difference. The pressure is on. This is the exact moment where your strategy matters more than your raw intelligence. Let's contrast their approaches, because this is where the marks are won and lost. On the left, we have Alex's answer. Now, Alex studied hard, really hard. But Alex has overloaded the page with every single raw physics fact they could possibly remember about electricity. They've written a massive paragraph about protons, electrons, historical models of the atom, you name it. But there is absolutely zero targeted analysis. The examiner's red pen is just everywhere crossing out irrelevant sentences. Alex essentially threw spaghetti at the wall, hoping something would stick. Then, on the right side, we have Sam. Sam panicked. Sam rushed through it, wrote one brief, vague sentence like, voltage pushes the current, and entirely missed the specific command word requirements of the question. Memorizing textbook wording completely fails when you don't know how to deploy it strategically. Neither Alex nor Sam is getting top marks here. Not because they don't know what electricity is, but because they haven't learned the actual architecture of a perfect physics answer. They don't know how to play the game of the exam.
So, how do we fix this? That brings us to Section 2, the four-step framework to build your answers. This is where we stop guessing what the examiner wants and we start strategizing. Listen, top-tier students, the ones scoring those A stars, they don't just know physics, they know how to systematically break down the specific assessment objectives expected by Cambridge examiners. They look at a blank set of dotted lines on the page and they see a specific structure they need to fill.
Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's get into the exact strategy. This framework is your gateway to full marks. Step 1, point. You need to explicitly identify the quantity or phenomenon. Don't beat around the bush, name it. Step 2, evidence. State the mathematical or physical relationship involved. What interacts with what? Step 3, explanation. This is where you explain the underlying physics driving that relationship. And step 4, link. Connect it back to a real observation, a specific experiment, or the actual device mentioned in the question. This maps perfectly to the famous PEEL framework: point, evidence, explanation, link. It forces you, absolutely forces you, to combine both your theoretical understanding and your practical application. And let me tell you, that combination is exactly what the 0625 syllabus demands. If you leave out the link, you lose the application mark. If you leave out the explanation, you lose the reasoning mark. You need all four.
Now, what's really interesting about this slide is seeing this theory in practice. We're going to do a 30-second interactive challenge right now. I want you to read these two options and spot which one successfully uses our new PEEL framework. Look closely at option A. It quotes a process. It says electrical energy is transferred to heat energy. Okay, true enough, but it completely fails to link it to a specific physical effect in the circuit. It's just a floating, isolated fact. It's an Alex answer. Now look at option B. It systematically hits every point. It identifies the phenomenon, potential difference. It states the relationship, energy transferred per unit charge. It explains the physics of the charge actually moving through the resistance. And then it links it directly to how this specific real circuit component, let's say a heating coil, functions. Option B is the undeniable clear-cut winner. That is what a full-mark paragraph looks like. It is tight, it is logical, and it leaves the examiner no choice but to award the marks.
Moving on to Section 3, Cause and Effect and Driving Physical Outcomes. When we apply our newly discovered PEEL blueprint to Alex and Sam's previously flawed answers, a magical transformation happens right on the page. We guide them to rewrite it. We tell Alex to cut the fluff and focus on the command word. We tell Sam to expand their single sentence using the 4 steps. And suddenly, those glaring, awful red pen marks transform into satisfying green check marks. By structuring the answer, we force the physics to make absolute logical sense. We aren't just reciting, we are arguing a physical case.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Now, I want you to burn this golden rule into your memory. Insist on cause and effect rather than isolated facts. Seriously, write that down. Whether you are dealing with magnetic fields, gravitational forces, subatomic particles, or complex parallel circuits, physics is entirely about physical outcomes. A causes B. A temperature increase causes a resistance drop. A larger potential difference causes a larger current. If you just list facts without connecting them with therefore or because, you aren't actually doing physics, you're just doing trivia, and Cambridge examiners do not give A stars for trivia.
So, the crucial point is how we define our terms once we actually understand the physical intuition behind them. Now that we know why we need this concept, here is the formal vocabulary you have to use. Potential difference is defined as the work done per unit charge moving between 2 points. Let's break that down. Work done means energy transferred, measured in joules. Per unit charge means per coulomb of electrons, so it's literally joules per coulomb. It is the active, driving cause that pushes the effect, which is the current, the flow of those charges, around a circuit. You are taking your everyday informal language like the battery pushes the electricity, and you are tightening it into sharp professional physics vocabulary. This is how you sound like an expert on paper.
All right, Section 4, Escaping Exam Traps. We're about to shift gears and turn this explainer into a full-on interactive workshop. We are going to test your new structural knowledge against the absolute most common weaknesses that Cambridge examiners report seeing year after year in their examiner reports. Grab a piece of paper or just clear your mind because you're about to be tested. Here is your very first challenge. Imagine you are in the exam hall, you turn the page and boom, you are hit with this data table. You have 60 seconds on the clock to interpret this data. Let's look at it together while the virtual clock ticks down. We've got resistor X. It has a voltage of 6.0 volts across it and a resulting current of 2.0 amps flowing through it. Then we have resistor Y, a voltage of 12.0 volts and a current of 4.0 amps. Look at the numbers. Don't just stare at them blindly. Analyze the relationship. What is the core cause and effect trend happening right here? Notice what happens when we move from resistor X to resistor Y. The potential difference, the cause, the push, goes from 6 to 12. It doubles. And what happens to the current, the effect, the flow? It goes from 2 to 4. It also exactly doubles. So what have you just discovered in under 60 seconds? You've proven that the relationship is directly proportional. As the potential difference doubles, the current doubles.
Furthermore, if you apply Ohm's law in your head, V divided by I gives you resistance. 6 divided by 2 is 3 ohms. 12 divided by 4 is 3 ohms. The resistance is constant. You've just extracted the physical, mathematical reality from raw, intimidating data. That is exactly how you tackle a data analysis question. Awesome job on that. Now, challenge number 2. This is a classic exam trap. A student is asked to explain a circuit's behavior, and they just write down V equals IR and move on to the next question. They think they've nailed it. But simply quoting a formula loses you massive marks if you don't link it to a physical effect. Listen to me carefully. The examiner doesn't want to know if you memorize the letters of the alphabet. They want to know if you actually understand that V represents the energy driving the charge, I is the rate of that charge flowing, and R is the opposition to that flow. If you just write V equals IR, you get nothing. The safe method, the guaranteed mark-winning method, is always our 4 steps: definition, relationship, explanation, and application. You state the formula, yes, but then you explain what those variables physically mean in the context of the device in the question. All right, challenge 3, the speed round. You have exactly 30 seconds. In your head right now, or scribbling furiously on a piece of paper, I want you to draft one perfect Peel paragraph applying potential difference to a real-life situation. It could be electrical engineering, it could be safety mechanisms, medical technology, or even just a simple flashlight you keep in your kitchen drawer. Ready? Start with the point. Identify the quantity. Then the evidence. State the energy relationship. Then the explanation. Explain the physics of the charge moving. And finally, the link. Connect it to the actual device. The clock is ticking. Keep going. Think about what's actually happening to the energy and time. Got it? If you manage to connect the abstract physics of potential difference to, say, how a defibrillator dumps a massive amount of energy per unit charge to restart a heart, or how your phone battery transfers chemical energy into electrical work to light up your screen, if you can make those links, you are thinking exactly like a top-tier, A-star Cambridge student. You are seeing the physics in the real world. Which brings us perfectly to our final section. Section 5, Quick Recall Mastery. We've done a ton of heavy lifting today. We've torn down bad habits, we've built a new framework, and we've practiced it. So now let's bring everything together into a concrete, actionable cheat sheet of rules that will guarantee you those top marks when the pressure is on. This brilliantly illustrates the ultimate system for your exams. Here are your 3 absolute, non-negotiable rules. Rule 1, command word decoding. You must always know what the verb in the question is demanding. Are you being asked to state a simple fact, describe what a graph looks like, or explain the complex physics behind why it looks that way? They require totally different answers. Rule 2, PEL framework application. Never, ever leave a physics fact floating alone on the page without an explanation and a direct link to the scenario. Anchor your knowledge to the question. Rule 3, time management matrix. Look at the marks available. Don't write a whole novel for a simple 2-mark question like Alex did. You'll run out of time for the rest of the paper. And conversely, don't write a single lonely word for a 4-mark calculation and explanation question like Sam did. Let the structure and the marks dictate your success.
To make all of this stick permanently in your brain, here are the 4 highly actionable revision prompts you should use for literally any physics topic, but especially for potential difference. Number 1, what is the core idea? Just explain it simply, like you would to a 10-year-old. Number 2, what changes physically? Identify the cause and effect. Number 3, what quantity, formula, or graph proves it? This is your evidence. And number 4, where is it used in real life? This is your application link. I highly recommend you pause the explainer and screenshot this mental checklist right now. Keep it on your phone. If you can answer these 4 prompts aloud for any given topic in the syllabus, I guarantee your knowledge is secure enough and deep enough for any short answer or structured question Cambridge can possibly throw at you.
Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCSE and click that bell. Don't let another exam pass you by.
Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.